Okay, I think we're rolling. So I just had a quick, I was like, oh shoot, we need to do a review, more of a summary of what we did, right? But just as a quick review, we talked about distinguishable permutations. Distinguishable permutations. Right, so when we have the word, we looked at the word assist. For example, how many distinguishable permutations can we have here? We treat all of these as if they're their own letter, right? And then we divide by however many recurring letters we have. Right. Then we moved on to combinations, which includes the choose function, the choose function. I don't actually know if it's called the choose function. Oh, the ATM question or the car button lock question be considered a permutation? No, so those ones would be just kind of, I guess just counting questions. Game over, near-death experience. So because it doesn't explicitly say that numbers can't be repeated, then we can just use the fundamental counting principle, or what's it called? I think it's called the fundamental counting principle, where we can just make little slots, and we'll look at some today again, so maybe I assigned it too soon. Anyways, you guys are working too hard. So we'll look at some, but yeah, so 12.1, but I think we also introduced the fundamental counting principle there, where we basically just multiply everything if things aren't, if there's repetition, right? So if things are being reused, so if the same number can be used multiple times, which it would have to say if it can't be. So that's the glitch. Oh, the menu one I haven't had a look at. I haven't had any questions about the menu one, but I'll have to have a look at that one. When did I make those due? Did I make them due too soon? This Friday. Not bad. Should be okay. I can adjust it if we need to. Okay, so let's just go through the summary from last day. And then in 12.3, right, we're gonna see a bunch of these questions put together, which is probably what you're seeing also in 12.1 and 12.2. So then hopefully they'll help a little bit. Okay. So we looked at combinations, we looked at the choose function. N choose R is n factorial over r factorial times n minus r factorial. Or just, or NCR on your calculator. Okay. So, what I did for today, just to keep going with the 12.3 examples, I just briefly typed them up, and on Moodle I posted the Word document as well as the PDF. I don't know if you guys if you're typing, then it's easier to copy paste from a Word document, I guess, but usually I don't use Word, but for you guys, I'll do it. And because it was really short. I usually do stuff in LaTeX. Have you guys heard of LaTeX? It's a typesetting language. Usually I'm in LaTeX, but it's not as easy for you guys to grab from. So what I'm gonna do here is we're just gonna, I'll make a little bit of room here. I still find that spelling of license with the 2 C's kind of irksome. Is that the American way? It just was the auto-corrected way. But now I'm like, I think I want an S on the end. But anyways, 12.3 continued. So the license plate situation is a lot like the ATM and the car door combination, right? I say combination, but not necessarily a combination, right? And so the license plate, the reason I say that is because license plates, it's kind of understood that you can have repeating digits or repeating letters, and that'll still be allowed, right? So someone could have a license plate AAA111, right? And that's allowed, right? Which means because we've got this repetition, right? It's not a permutation and it's not a combination. It's going to be something different. And so I will say, so because I did have a question about the ATM one and the car door one. So I kind of had to stop myself and think, well, why did I know that there was allowed to be repetition? And basically the answer is, unless it says explicitly no repetition is allowed, like repetition is not allowed, then you should go ahead and assume that you can have repetition, right? So it's one of those things, I've read so many of these problems, I've done so many of these problems that I know that they'll have to say something at some point about, okay, you're not allowed to repeat digits, for example, you're not allowed to repeat letters. Okay, so I will make a note here that unless a problem states explicitly, right? Or for some reason, oh, you have to push 6 buttons to open and now what's a 5-digit code? That's weird. The one I saw had 4 digits and a 4-digit code. So they must be, okay. Push each of the 6, yeah. What they mean is with the 6 buttons, so some automobiles have 6 button locks. To gain entry, push each of the 6 buttons in a particular order to unlock the door. How many different 5-digit codes are available? Yeah, wording is not great, but what they're saying is you've got 6 buttons to choose from, and then you're going to make a 5-digit code out of that. Right? So for each of those 5 slots, you're going to have 6 to choose from. 1, 1, 2, 3, 4, 5. If it has to be a 6, yeah. Yeah, so if it has to be a 5-digit code, it can only have 5 digits, of course. But if you're choosing from 6 digits, then that's how many choices you have per slot. So here's the key, though. 2, 3, 4, 5, 6. Yeah. Unless a problem states explicitly, so they would have to say repetition is not allowed. That repetition is not allowed, we can assume repetition is allowed. Okay, so here, because it doesn't say 3 letters followed by 3 digits, right? 3 letters without repetition followed by 3 digits without repetition. It just says 3 letters followed by 3 digits. So what you're gonna do to solve this one is, and this is what I mean by slots. So for the letters, right, let's assume just the English alphabet, we have 26 letters, right? And then, so just that's an assumption that we're making, right? And then for the digits, we've got 0 through 10, or not 10, 0 through 9. So we have 10 digits to choose from, right? So what we have is we can make slots. So if we want to make a license plate, then we're going to have a letter, a letter, a letter, followed by 3 digits, 1, 2, 3, digit, digit, digit. So this is how you're going to approach things if repetition is allowed. Right? So if repetition is allowed, then typically, and we'll see some examples where it's not quite true, where we might have to multiply these and add them to these guys multiplied. But for now, because they're all just happening at the same time, then we multiply all the way through. Okay. So here, we multiply through to find the total number of possibilities. Total number of possibilities. Possibilities. Okay. So we said we had, just to emphasize, we've got 26 letters. Okay. If repetition is allowed, then for the next letter, I still have 26 letters to choose from, right? 26, 26. And then for the digits, I've got 0 through 9. So I have 10 digits to choose from, 10, 10, 10. So if I multiply through here, what I get is 17,576. Sorry, 17,576,000 different possibilities. It's a lot of license plates, right? I think there are probably some license plates that aren't allowed, so they would get pulled out, but we're gonna pretend that they don't exist. Okay. So for the next one, if we have 3 digits followed by 3 letters, if we just have a look here, that's going to be the same, right? We're just multiplying in a different order, right? But let's just show it and have a look. So for B, now I've got a digit, a digit, a digit, followed by 3 letters. So I've got 10, 10, 10, 26, 26, 26. If I multiply these across, I get 17,576. This is the same as A. And I've got it a little bit further down, right? But if we just stop to think, okay, well, And BC did this, right? I think, I can never remember which one they used to have first. TNW, I think it was digit, 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 letter, letter, letter. And then when they ran out, they had to switch to letters first and then digits. And then just sort of recently, they started with the letter, letter, digit, 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 letter, or is it letter, digit, digit? Anyways, who can keep track? No, I do have like a weird fascination with license plates. So anyways, so this section's really working out for me. But no, so I used to keep track. But anyways, doesn't matter. But if both of these that we're talking about, right, letter, 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 digit, 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 say that 3 times fast, and then and digit, 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 letter, 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 if they're allowed to be in circulation at the same time, right, then we're looking at these two possibilities added together, right? So you just have to kind of look at it and say, okay, well, I can have all these combinations, right? Or I can have these combinations. Thinking back to sets, right? Whenever I'm saying or, typically I'm going to be adding, right? And then if I'm saying and, I'll be multiplying. So that's just kind of a quick rule of thumb. It usually works, but yeah, not always. Okay. So if both of these can be in circulation at the same time, then the total number of possibilities is the first one plus the second one, right? And I think you guys had something sort of similar for the seating arrangement one. Can't quite remember. Anyways, sort of similar, not 100%, but sort of. For part C, right, we're gonna have 1 digit followed by 3 letters followed by 3 digits. Okay, so now we're adding a digit in front. And so C, if we have a digit first and then a letter, 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 followed by 3 digits, again, no mention of repetition isn't allowed or anything like that. Well, I can cheat a little bit here and say, well, I know what this equals, right? 17,576,000. So I have to multiply it by 10. There's no harm in just listing them all again and going through that calculation again. But sometimes it's nice to find these little shortcuts and just kind of see them, that they're allowed. Oh yeah, so I'll say usually, right? Usually, if you find yourself saying and in a situation, right? Letter and letter, right? And is going to be multiplying. You will be multiplying. Okay. Whereas or is usually addition. So this or this, right? Then I'm adding. Or usually means addition. Cool. So usually it's just a kind of a quick rule of thumb. The reason I say usually is because sometimes we use and or kind of incorrectly, but for the most part, if you just kind of take a step back and say, okay, well, this has to happen, and this has to happen, and this has to happen, then you're going to be multiplying those possibilities. Okay. So here, going back to C, if I get 10 times 17,576,000, puts me at 175,760,000. And then so here, part D, all of these in operation at the same time, right? So all in operation at the same time, just because it's kind of far up the page. Just to illustrate with that and or situation, you could have letter, 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 digit, 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 or I'll scoot this over, or digit, 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 letter, 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 or digit, letter, 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 digit, digit, digit. Because the license plate can only have one of these, right? So that's why it's or. So here, this was 17,576,000. Or means plus 17,576,000 plus 175,760,000. Giving us a total of 210,912,000 different license plates. Different license plates combinations. You kind of have to be careful with the combinations, right? Combinations, we use that word, and it doesn't really mean what the mathematical combination means, right? A mathematical combination is when you have no repetition and you have, 10 things to choose from, and you want to choose 4 of them in no particular order. Right? But that's not what we mean when we say combinations. So you have to be careful. Context helps. Okay. Any questions about that one? I haven't seen any. I'll go grab the next example. Put it on a fresh page here. So here, right, now, right, we're saying, okay, now repetition is not allowed. So it's here, it's stated explicitly that we're not allowed any repetition. Okay, so repetition is not allowed. Okay. There are 2 ways that we could solve this. So we want to find how many license plates with 3 digits followed by 3 letters are there, right? And so there are 2 ways to solve this, and they're obviously going to get you to the same result. So whichever one your brain goes to first, that's the solution that you should be kind of practicing and doing. I don't care which one you use. So There are two different ways of solving. Two different ways of solving this. So the first way is we could use those slots again, right? But just remembering about the repetition. So now we're not allowed repetition, so we can use slots again. So then we're allowed, okay, we have 3 digits followed by 3 letters. A digit, 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 letter, letter, letter. Okay. If repetition is not allowed, right, for my first digit, I have 10 to choose from. Right? But now I've used one, I don't know which one, it doesn't matter which one. So for my next digit, I only have 9 to choose from. The next digit, I've already used up 2 of those digits, so now I have 8 to choose from. Yeah. Same thing with the letters, right? I have 26 to choose from. Then I've used 1, so now I move to 25, and then finally 24. So if I do this, this becomes 11,232,000. This, though, right, now I've got this permutation, right, where I don't have any repetition, so it's either a permutation or a combination, but now the order matters, right? So this is a permutation, and this is a permutation. So what I can do is my second way is use permutations. 10p3, right? I'm picking 3, and 1, 2, 3 is different from 3, 2, 1, right? So that's what I mean by order matters, right? Here, it's a permutation since I guess I could have done 3. 1, 2, 3 is different from 3, 2, 1, right? So now I can use permutations, but I have to keep in mind that I've got a permutation times a permutation, right? So now I've got 10p3 times 26p3. If you try it using the formula, or probably easier on your calculator, right? You've got that p function on your calculator or Google or whatever, you're going to end up at the same results, in the 11,232,000. Yeah. I don't know why I put an arrow on the 2. I'm going to remove that. I guess it was just my thought arrow. Or you can do this. So we've still got kind of this, this non-combination or permutation here, right? Because first we have to have 3 digits and we have to have 3 letters in order to make this complete license plate, right? And so we still have to multiply these across. So it's kind of like 2 permutations put together. I'm gonna grab the next example, but if you have any questions about that, you can throw them in the chat or, you know. So the next example, so you've got a choir and there are 6 sopranos, 5 tenors, and 3 basses, and you're gonna select 1 soprano, 2 tenors, and 1 bass. Right? And so how many ways can this quartet be formed? Well, let's see. So now, right, if I'm just picking 1 soprano out of 6, well, that's gonna be, well, there's no order there, right? Especially because I'm only picking 1, right? So it's gonna be 6, choose 1 soprano. So for part A, I've got a soprano spot, I've got the tenor spot, and then I've got a bass spot. A little bit different than what we were seeing, right? Could you go through and make the slots? I don't know, I haven't tried it out. Yeah, because it doesn't matter which order I pull the tenors from, these are going to be combinations. And so what I'm doing is I'm going to fill these spots with 6, choose 1. That's the soprano. So I'm from 6, I'm choosing 1. And then from the tenors, I've got 5, choose 2. And that's where my 2 tenors will come from. The difference between A is that the tenor spot, so the tenors that are chosen, right, it doesn't matter who, if they're chosen into the group, they're in the group, and if they're not, then they weren't chosen into the group. So those 2 tenors, there's no order there. Whereas if we glance ahead at part B, what if one of the tenors is designated lead tenor? Then order matters, right? Then the first tenor is going to be the lead tenor, and then the second one that I chose is going to be whatever second tenor, I don't know, right? And so now order matters in part B. But for right now in part A, we're just saying from these 5, you're going to choose 2. Order doesn't matter, and so it's a combination. Let's see here. Combination. I'll extend this little, since order does not matter. And then for the bass, we're selecting 1 bass from 3. 3, choose 1. And this on your calculator is going to be 6C1 times 5C2 times 3C1. Or you can use the formula and get to the same thing, but it's a little bit more work. Puts us at 6 times 10 times 3, which is 180. That's right. Yeah, so a number choose 1 is just always going to be that number. So now, part B, now the tenor slot is a permutation since order matters, right? And so we've got the soprano, the tenor, and the bass. We already figured out that there are 6 different ways to choose the soprano and 3 different ways to choose the bass. And so here for the tenor, this is going to be 5P2. And there are 20 ways if order matters. Right? If Bob is lead tenor and Doug is not, right, that's different from Doug being lead tenor and Bob is not. Okay. So this becomes 6 times 20 times 3, which is 360. Okay. So for our last example from this stuff, we've got a deck of cards, and we want to find the number of ways of obtaining at least 1 diamond when drawing 5 cards from an ordinary deck of cards. This is really hard, right? If you think about, okay, well, what do I have to do here? I have to have at least 1 diamond. Okay, so I could go through, and notice that I say could. I'll show you the trick in a little bit here. I could go through and figure out how many ways I could have 1 diamond, 2 diamonds, 3 diamonds, 4 diamonds, 5 diamonds, and add those all up. That's perfectly reasonable. But a lot of the times, if we're talking about kind of at least situations, we usually employ the complement, right? So I could figure out how many five card hands I have in general, and then just subtract everything that doesn't satisfy the at least 1 diamond. Because there's only one way that I could, or not one way, but kind of one situation, and that's if there's no diamonds in my 5 card hand, right? So then I can just pull those out of all the 5 card hands, and then I have the same result. Either way, if you want to, just work through it, right? Just remembering that at least 1 means 1 or 2 or 3 or 4 or 5, right? You'd have to figure all those out and then add them up. Totally fine. Should get you to the same answer. Or you can find out all the total 5 card hands, subtract the ones that don't have any diamonds, and then basically the complement, right? The opposite. So this is not easily computed, right? So we can think about this as the total number of 5 card hands, the total number of 5 card hands minus all the 5 card hands with no diamonds. So the total number of, shoot. We don't have a mailbox yet, and I just saw the mailman walk by. I think he had mail for us, but he's teaching me a lesson. We have to put up a mailbox. Anyways, come back. So what we have to do is we have to figure out the total number of 5 card hands, which we've already done earlier, but it's a good exercise. And so the total number of total 5 card hands is going to be from 52, choose 5, right? 5 card hands is probably the only situation. So if you're pulling from a deck of cards and you're kind of dealing from a deck, then it's one of those situations where it's understood that there's no repetition, because if I've dealt my cards, right, I'm not taking cards back and redealing them, and then just kind of it would keep going and going and going, right? So if I'm dealing a 5 card hand, then there's no repetition, right? So that's just kind of a trick of the trade, I guess. So the total 5 card hands we've already found. I'll scoot this over, it's a big number, is 2,598,960. Okay. So now we can find 5 card hands with no diamonds. With no diamonds. I pull all my diamonds. There's 13 diamonds. So now I'm left with 39 cards to choose from, right? So I've got 39, choose 5. Number of non-diamond cards is the 39. Which is going to be 575,757. Hey, what a fun number. 575757. 39, choose 5. Lock that in. It can be my new favorite number. What's your favorite number? 39, choose 5. 575757. It starts on a 5 and it ends on a 7. But it's a good number. Thanks. Or maybe a really bad number. So we find 2,598,960 minus 575,757 is 2 million again, but just a little bit less. 2,023,203. Well, it is a fun number, and also 2,023,203, also a pretty fun number. So we find 2 million blah 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 weighs drawing at least one diamond, diamond in a 5-card hand. Okay. What's the other way you could have done this? Kind of the hard way to solve it. It works just as well, right? It's just going to be more work. No, too much work for me. But the other way, but I'll read it as I'll leave it as an exercise to the reader, as the textbooks always say. We'll leave this as an exercise to the reader. Using real cards, real application. So the other way to solve this would be to find the number of 1 diamond hands plus 2 diamond, probably 52. Yeah, like I said, I haven't worked through it because you would have to have 13 choose 1 times 39 choose 4 plus 13. No, but then you're left with 12 because you've already picked a diamond. 12 choose like I said, it's hard. Nope, fresh hand, 2 diamonds, 13 choose 2. Yeah, it's hard, I'm telling you. That's why I showed you the easy way. Plus 2 diamond, plus 3 diamond, plus 4 diamond hands, plus 5 diamond. Okay. Or you can just say the total number of 5 card hands minus 0 diamonds. It's the same. 1 diamond should be 13 choose 1. You have to have 1 diamond times 39 choose 4. You need to keep going and going and going. Might be fun. You know what the answer should be, right? It should be this 2,023,203. But a lot more work, right? I give up. Should I tell you guys a secret? I've got a pile of junk behind me. But I was like, oh, smush it in. Yeah, you guys should see down there. It's not pretty. We can't all have these virtual whatevers going on. I guess we can, but I still don't know how. And that's okay. And that's okay. On the floor where they belong. are we done with combinations and permutations or what?
I actually have a question, Emily.
Sure. Let me turn up my volume here.
Okay. So okay, my first approach to this question, even before you started explaining, was okay, so I need to choose at least one diamond card for my hand. So that's 13 possibilities for the first slot.
Mm-hmm.
Then I have my one diamond. I don't care what the rest of the cards are. So for the second slot, I have 51 possibilities, then 50, then 49, etc. And of course, I arrived at the wrong answer. Is there something I'm missing there? Is there something, if you have 51, that includes diamonds? That's kind of my point.
No, I see what you did. I think it's good. I just what I suspect is going on. So you're forcing one, and then you're allowing for the possibility of all of these to just be one diamond, right? So you're not forcing two, you're not forcing three. So you would do the same thing. But you'd have to make sure that the others weren't, yeah, so I see what you mean. And I see the kind of thinking, having a hard time arguing against it. I have a feeling that it's wrong because you're not forcing 1, 2, 3, 4, 5.
Yeah, the math arrives at the wrong answer, and the math doesn't lie. So, you know.
That's why we love to hate it, right? But yeah, shoot, I'll have to think about kind of the actual reason why it doesn't work. Yeah, let me stew on it. Okay. Cool.
Thank you.
Got it. All right. Let's leave permutations, combinations, and everything in between behind us for a little bit. We'll have to do it on the test, but no more new stuff. We are moving into chapter 15. Bouncing all over the place here, which is on graphs and functions. It's going to be a nice little, probably sort of break after what we were just doing. Today we're talking mostly about straight lines, linear equations, all that fun stuff. So from the textbook, we're only going to do, so from the textbook, we're doing 15.1 and 15.5, just as a heads up. And A10 is chapter, we're in there. Ace, king, queen, jack, 10 is different from. Yeah, I feel like, anyways, I'll have to think about that next day. I need time. Okay, so we'll start with just kind of talking about lines, Cartesian coordinates. It's got a fancy name, but really it's just the XY grid that we're all kind of familiar with, hopefully. And if you're not, this will be a nice refresher. So probably even as we go through it, should feel kind of familiar. So the Cartesian coordinates and graphing lines is the first section, and then the second section talks about actual functions and their graphs. And then after that, we're gonna kind of, I'll just give you the material so just our notes for the next little bit for chapter 15, which is one-to-one and onto functions and function composition. Those will be just in our notes, and I'll make a note in our notes about that. But that won't be until probably next day or the following day. Ooh. Did I say anything about a test earlier? By your faces, the ones I can see, I'm hearing a no. Okay. Oh, well. We've got two options. First option is the day before Thanksgiving or the day after Thanksgiving. And I'm open to suggestions, whatever you prefer. Me, when I'm a student, I want to have the test before a break so I can just kind of relax. I'm seeing a lot of befores. Hey, we're not that different after all. Yeah, so it feels like before might be a good, so that's what I'm aiming for here. Okay, so we'll do the, well, I piled all my crap on it, my calendar. But whatever the day before Thanksgiving is, let's see here. Where's my other calendar? So Thanksgiving is on the 12th. We meet Monday, Wednesday. So then that puts us on October 7th. Okay. So we'll have, oh yeah, nice. So are you guys okay with test 1, October 7th? Cool. I will put it way up here at the top in screaming pink letters. Test number 1, Wednesday, October 7th. It's going to be on chapters 2, 12, and 15, but really just only how much we've covered by, uh-oh, I need more space here. Only as much as we have covered. Oops. By end of day this coming Wednesday, the 30th. Okay. Which leaves kind of one day of review, cleaning up any questions you have. So everything that we'll have covered by the end of the day on September 30th will be testable material. Okay. But what you'll see from today at least is chapter 15 is kind of fun. So it's nice to have fun options, not just combinations, permutations. Okay. And I'll give you guys a practice test just because, to be quite honest, I don't really know how I want this test to or what I want it to look like quite yet. Probably involves something in WebAssign, probably some written work. Anyways, I'm just figuring it out. But I'll give you guys a rundown on the 30th what to expect for the following week. Okay. All right, 15.1, Cartesian coordinates. Oops. And graphing lines. And graphing lines. And remember too that, well, I'll give you guys a practice test, right? But also assignments are gonna be quite a bit harder than test questions. And that's in general, right? So, because assignments, you have time and you can look things up and you can ask each other questions, you can ask me questions. Whereas a test, of course, I know it's, you know, you're under pressure and that kind of stuff. So it's, a test question is never going to be as hard as a hard assignment question. Okay. Hooray. Just keep that in mind. Oh yeah, I call them tests. Sometimes people freak out if you call them midterms. There was one term where I just called them like a check on how much knowledge you have up until this point, because the terminology, it just kind of, so I just yeah, it's the midterm. I guess by definition it can't be the midterm, because a midterm, there should only be one midterm. Midterm. And we're doing more than one test, so I'm calling it a test. Yeah, quarter term, third of term, whatever you want to call it. Machiavellian. Whatever you want to call it. Call it what you want to call it. Yeah, the tertiary test. Yeah, there could be several middles, I guess, depending on how many times break it. Anyways. We're changing gears. So now we're going to be talking about XY coordinates, right? And so again, we need to develop a lot of terminology around this kind of stuff. And so what we say is, if there are two values, X and Y, if there are two values, X and Y, that make an equation true, then we say the ordered pair, XY in round brackets, and we saw ordered pairs just briefly in the Cartesian product, right? The Cartesian product yields many ordered pairs. And so so round brackets around an X comma Y is a coordinate, and we call it an ordered pair. So we say the ordered pair X comma Y satisfies the equation. Oops. It's because I lean my hand on the bottom corner and it won't let me write at the same time. Satisfies the equation and that it is a solution, is a solution of the equation. Solution of the equation. Okay. So we have an x-coordinate and a y-coordinate, and if we just have some set of ordered pairs, we can figure out if they make an equation true, and that would make them a solution. So for example, determine if, if each ordered pair satisfies the equation, 3x minus 2y equals 7. First one is when x is 1 and y is negative 2. B, negative 2, 1, and C, negative 1, negative 5. Okay. So what we have to do is we have to plug in the first one, 1 for x and negative 2 for y, and if it equals 7, then it's a solution. So part A, 1, negative 2 into 3x minus 2y, does it equal 7? Okay. So what I do is I have 3x minus 2y, and then until I've shown whether it equals 7 or not, I try to put a question mark up there, up above the equal sign. And then what I'm going to do is I'm going to have 3 times 1 minus 2 times negative 2, 3 times 1. If I want to show my work, I can still have the question mark 7. Does it equal 7? Well, negative 2 times negative 2 plus 4. 3 plus 4 does equal 7. So therefore, 1, negative 2 is a solution, right? And satisfies the equation. Good. So let's do the same thing, right? Because in these pairs, right, the coordinate pairs, the order matters, right? 1, negative 2 is not the same as negative 2, 1, especially if we get into kind of our coordinate system, right? When x is 1 and y is negative 2, it's not going to be the same as when x is negative 2 and y is 1. But we'll see that in a little bit. So B, we had negative 2, 1. I'm going to do the same thing, and 3x minus 2y, does it equal 7? So now I'll just leave the x and y blank. 3 times negative 2 minus 2 times 1. Oops, does it equal 7? 3 times negative 2 is negative 6 minus 2, which is negative 8, which does not equal 7. Therefore, -2, 1 is not a solution. And then we can do the same thing again for C. And we can have -1, -5. Do the same thing again. So notice that even though it kind of seems a little bit, I don't know, tedious to write out the bare bones equation that I'm plugging stuff into every time, if I want to do things properly, I'm gonna show my kind of empty equation first and then fill it in on my second line. So it might be tempting to kind of jump in and just plug them in right away, especially for little equations like this. I'd say it's fine, but if you're dealing with a larger equation, then it's a good idea to just write your blank equation first, then fill it in every time. So I'm trying to teach good habits, but sometimes even I'm just plugging stuff in right away. Even I. 3x minus 2y, does it equal 7 if x is -1 and y is -5? 3 minus 2, and then just to emphasize, I've got -1, -5. Does it equal 7? So I've got -3. -2 times -5 puts me at +10, which actually does equal 7. Therefore, -1, -5 is a solution. Okay. If we just kind of, and we'll flesh this out a little bit more, but one thing that I'll get you to start doing is just recognize that this is an equation of a line, right? So if there's an x and a y and you can rearrange it, you'll be able to rearrange it in the form of y equals mx plus b, right? And so here, we'll start to recognize that this is an equation of a line. And I am jumping ahead, but it's just good to kind of point it out as we go. So this is an equation of a line. And so what does it mean for these points to be a solution, right? A solution is a point on this line, right? Any point that's not on this line is not going to be a solution. So a solution is a point on this line. So that's what that means. But like I said, we're going to flesh that out a lot. But first we have to establish the Cartesian coordinate system, which is just the XY plane that we're probably familiar with. So the Cartesian coordinate system the Cartesian coordinate system is formed by drawing two perpendicular lines, right, called axes. It is formed by drawing two perpendicular number lines called axes. Oops, x's, axes. So there's some terminology here, and we're going to go through and just kind of set up a Cartesian coordinate system. So first thing we said was, okay, it's a set of perpendicular number lines. Of course, they cross here at 0, 0, which is also called the origin. Anything to the right on the x-axis is positive. Anything to the left is negative. Same thing on the y-axis. Anything below the origin is going to be negative. Anything above the origin is positive. Hopefully that's ringing some sort of bell. So here we've got the x-axis, and here we've got the y-axis. Unless I'm very, very lazy, I'll always draw these arrows. Right? You'll see it if you ever caught a glimpse of my nasty notes on the side here. Sometimes I'll cut them out, but we should have arrows to indicate that, well, these are number lines. They extend to positive infinity and negative infinity, right? And so we should have these little arrows all around. Okay. So we can use this as a grid, or it is a grid, and we can put points all around, right? So let's see here. If we have a point called capital P, called capital P, at some point A, B, this is usually how we write it. So we have the name of the point first, usually a capital letter, and then followed by the coordinates. So this is PAB gives the coordinates, gives the XY coordinates of the point P, capital P. Okay. So what that means is that A is here on the x-axis, and B is here on the y-axis. You might also remember that there are 4 quadrants, right? Even just looking at this thing, this grid, right? I can see that there are 4 quadrants, but we use Q1, so this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Where Q just stands for quadrant. So if I tell you that something is in quadrant 3, right, then what I'm telling you is that your x's are all going to be negative and your y's will also be negative. Q3, both x and y will be negative in Q3. squeezing it in on the same page here. Okay. These are all things that I expect you to know, of course, but nice to have a little refresher. Terminology, fun stuff. Anything else that I should have put on here? No, these are the basics. So this is where I expect you to kind of be at least. Okay, so like I said, it's going to be really helpful to be able to recognize. So if I give you an equation, it's going to be really useful to be able to recognize a straight line, right? And a straight line is just going to be if you have an x and a y and that's it, right? So no x squared or y cubed or anything weird like that, right? There's just an x and a y. Right? So it will be helpful to be able to recognize an equation of a straight line. Okay. Anything with 1x and 1y, right? Or it's any equation with x and y as its variables. Okay. The first form is the standard form of the equation of a line. The standard form of the equation of a line is ax, so capital AX plus capital BY plus C equals 0. Okay. So just looking at this, right, A, B, and C would just be real numbers, so they can be anything. But like I said here, right, it's any equation with x and y as its variables. So if you're able to kind of collect like terms and regroup things and have just in the format of ax plus by plus some constant, right, then you're looking at a straight line and you're looking at solutions on this straight line, presumably. Okay. So, now for the blah, right? Where A, B, and C, where A, B, and C are real numbers. A and B, both not 0, right? If A is 0, then there's only a y, and if B is 0, then there's only an x, and so now I'm not looking at x and y as my variables anymore, and so they're gone, right? So that's another condition, is that A and B both not 0. And xy, right, the ordered pair xy, or the coordinate xy, is any point on the line. Okay. I should have started putting rings around it, because I put a square around it because it's good, it's important. I like it. Should put a ring on it. So, just some more terminology. I have never called this a first degree equation in two variables. I never will call it that. But it can be called that. So I'm going to tell you, in case you're reading something and you see something that says first degree equation in two variables, I'll call it a linear equation. So I will own up to that. So this equation is called, first we can call it a first degree, like I said, I'll never use this, first degree equation in two variables. Or the second way is a linear equation in two variables. But honestly, if it's a straight line, it's kind of implied. So I'll use this one. Terminology you can use. No, isn't that like a campaign slogan? Terminology you can use. Terminology I will use. Okay, is a linear equation. Just an equation of a straight line. Straight line, blah, blah, blah. Okay. So this is the standard form of a line, right, of a linear equation. But you might be more familiar with the point slope form, or the slope-intercept form. Sorry, that's a different form. You might be more familiar with the slope-intercept form of a line. Might be more familiar with the slope-intercept form of a line. Which is the y equals mx plus b. Probably sounds more familiar from hopefully high school. Right, where m is the slope and lowercase b, right? So the case of these letters is going to be important, right? Lowercase b is the y-intercept. For some reason, y equals mx plus b really took off. There must be some reason why they just started teaching us y equals mx plus b, but really, I'll erase this later, but in stats, you would use y equals ax plus b, or y equals b1x plus b naught. They all look the same, right? So as long as you've got something on your x and something on its own, these are all straight lines, right? So we need to start recognizing that. So, all right. I guess I should put a ring on it. One thing to notice, right? if you can rearrange things into either standard form, kind of boring, or into slope-intercept form, either way, you're going to have a line. And one thing to notice that if we do have ax plus by plus c equals 0, right, the standard form, I can rearrange this into the slope-intercept form, right? With a little bit of work, solve for y to get this from standard form into slope-intercept form. Right, so I've got ax plus by plus c equals 0. If I'm solving for y, then I can move the ax and the c over to the right-hand side by subtracting them from both sides. So I have by equals negative ax minus c. So far, so good. Gonna get a little bit nasty, right? Because I'm dividing by b, but that's okay. So y is going to be negative ax minus c over b. I'm allowed to break this up, right? Break up the denominator. So I have negative a over b times x minus c over b. I'm allowed to do that. With that common denominator, I'm allowed to break them up. Rules of fractions. Okay. So now you'll recognize that this is now in the slope-intercept form, right? Where the slope is going to be negative a over b, and the intercept, the y-intercept. Often if I say always if I say intercept, I mean the y-intercept. If I mean the x-intercept, I'll say x-intercept. But that's just, I don't know. That's just me, guys. So the y-intercept is going to be negative c over b, right? Because it's y equals mx plus b, so that negative c over b is my y-intercept. Okay. So we can rearrange these going from standard form into slope-intercept form, and remembering what the slope is and what the y-intercept is, not something that I expect you to do, right, or memorize or anything like that. You can easily do this and figure out what the slope and the y-intercept are, so not worth memorizing at all. Right? It's just looking at these and saying, oh, I can easily rearrange this probably into slope-intercept form, because that's what we like to work with, right? But like I said up here earlier, when we were looking at this equation here, 3x minus 2y equals 7, I can rearrange this and I can solve for y, right? Might end up a little bit nasty, but that's okay, right? I can still solve for y and I can put it into slope-intercept form, or I can move the 7 over to the left-hand side, and then all of a sudden I've got it in standard form, right, already. So either way, it's going to be really useful just to be able to recognize straight line equations, right, or linear equations. Okay. So let's talk about slope. Probably remember rise over run. We're just going to re-emphasize that in just using the coordinates. So the slope of a line passing through the points, oops, through the points x1, y1, and x2, y2 is the steepness of that line, right? So kind of the pitch, I guess, is the steepness of that line. Okay. So we'll use m for the slope. The slope is m, which is just rise over run. Okay. If I convert this in terms of x1, y1, x2, y2, right, this is going to become, and what I'll do is I'll just kind of draw a quick line here. x1, y1 is a point, and just to make things easier, I'm going to use a positive slope. We'll talk about positive and negative slopes, but I'm going to use a positive slope. And so here's my x2, y2. Yeah. So now I'm going to draw a straight line through here. Wow, what a straight line. Cheating. Okay. So if I want the rise over run, then what I'm looking at here, this is the rise. And if I have to calculate it, right, the rise is going to be y2 minus y1, right? The rise is y2 minus y1. And then here, this is the run. The distance between x1 and x2, right, is going to be x2 minus x1. So if I have rise over run, really what I'm saying is that I have y2 minus y1 over x2 minus x1. And just some things to keep in mind. This, if I have a slope like this is a positive slope. Right? That's if m is greater than or equal to 0. I'll say, how about just greater than 0, right? Then I've got this upward facing line. If I've got something like this going downwards, then I've got a negative slope, which is if the m itself is actually negative, right? So if m is less than 0. If there's no slope, what does that mean? So if m is 0, if m is 0, right, then on my coordinate grid here, if I've got a slope of 0, right, then we've got a flat line here, right? Maybe y equals 3. Oops. Right. So now I've got this horizontal line, and I don't know if you guys struggle, but I have a hard time, or I used to before this trick, I had a hard time with horizontal and vertical. But for horizontal, I just think of the horizon, horizontal line, and the vertical is just the opposite. You only need to keep track of one. That's like for so many things. Anyways. So same with the less than, greater than. Have I told you guys the L trick for that one? Can't remember if we've done a lot of inequalities. I'll write it on here. Less than. Yeah, so so the alligator eating the bigger amount, if that works for you, that's awesome. For me, I'm like, so if I'm the alligator, then I don't know, I always found it really confusing. And these are things that we need to know, right? We need to know the less than, the greater than. And so same thing here, right? You can just read it. So you take your L, your loser finger, and then you plop it down, and if it looks like an L, then you can read it as M is less than 0, right? Anyways, I find it more helpful than the alligator, but if the alligator works for you, then you're more clever than I am. Anyways, this way you can just read it across. And then if it's not an L, then it's greater than, M is greater than 0. Right? So if the slope is 0, then we've got this horizontal line at whatever the y-intercept is. If m equals 0, we have a horizontal line at the y-intercept. Those are our options. And I think that's a pretty good place for us to stop. What do you guys think? A little bit early. I've never found a student who minds, including myself. Yeah, time to go make a sandwich. Oof, yeah, get that garlic in the ground. Yeah, we've got better things to do. Next day yeah, that's not fun. Don't go to work. You don't gotta go to work. You can work from home. Aw, they give you lavender? That's really nice. Anyways, any questions about this stuff? We'll pick up here. We'll start graphing lines and just kind of solving linear equations next day. All right. See you guys later. See you Wednesday.